All right. Hey guys, I'm going to talk about sort of an intro to RNNs and then a little bit of, or sort of an idea of RNNs I've been playing with for some research that I've been doing. And then my name is Matt. I'm a senior doing computer science and biology. So just a brief intro on RNNs. I'm not going to go super in deep, so just like the idea of them. They're designed as a sort of a way to do a way to model sequential data. And so at every time step, you have a different input and output, and then you have a hidden state for every time step. So I can see here you'd have like the input X and then the hidden state, which gets changed every iteration, and then you have some output L. And then you would train the weights of this model to affect like what is essentially predicted for the output. So sort of breaking it down more here. You have some input layer and then hidden layers. You can have one hidden layer, you can have more. Just will stack RNNs. But essentially you just have some kind of like trained layer here that decides on what's going to be remembered versus forgotten as far as like as when the time steps increase. And so ideally you would have some perfect trained layer that can know what to forget and what to remember. So it can accurately predict the next for like the outputs up to like a million time steps. And so again, here you have like the input, the hidden layer, and then you keep updating this as you have more time steps. And so there's some variations. The first kind of basic one is this RNN here. You can have a different activation layer like tan H or a sigmoid function. But the idea is that you have your hidden layer from the previous time step right here, and then that is combined with the input, and then some nonlinear activation, and then you would have um, that would form the like time step of this next hidden state. And so one variation of that is LSTMs. They're called long short, or they stand for long short term memory. And so you have this mix of functions here that are supposed to be better at remembering and forgetting certain inputs so that they don't cloud what is actually relevant to like the current time step. And another variation of that is the GRU, the gated recurrent unit. Same idea where you have some combination of activation functions that should ideally forget irrelevant information and remember important information. And so some things that this is used for would be like a lot of time series data. So like financial forecasting, like stocks, so you have a year of stocks and you have like all the in and out prices. Then in theory, that could help you predict like the next day's stocks. Similarly, you can do like weather and NLP. There's a lot more other areas like this is used for, but these are just some examples. So that's the gist of it. You have a sequence of inputs and you want to know like the output, the different time steps. And then are there any questions so far? So then the big idea or the new idea here that I've been playing with is called test time training. And so the idea is that at test time, you are training the model as opposed to training it beforehand. And so the goal is that, or the sort of motivation is that you would have like so you have five time steps, and in those time steps you have some inputs and that affect what comes next. It's better to update that during the actual testing process so that you're getting like a more up-to-date sort of history as opposed to training on other like data sets that are maybe not necessarily reflective of your data set. So for some background, transformers, which I think someone might have talked about here, they're really good for long sequences and they have the best performance. But the problem is that they get increasingly slow as the sequence length increases. They have the quadratic complexity, and that's because of the key value cache. And so it's really good for a lot of domains like I have listed here. But the problem is that, again, as like you get really long sequences, this grows really quickly. And so it's got really poor performance for long sequences. We ideally like to have a linear time or subquadratic time for this. So that's where the test time training comes in. So again, RNNs are not good at compressing a long context into their hidden state. And in these examples, you have like a hidden state of a fixed size. However, with transformers, you have a growing hidden state or the analog of a hidden state. And this is what's really helpful, but again, that's really inefficient. So we want to have our hidden state be really good at understanding what's important to remember and what to forget. So that is what TTT brings to the table. So the main observation is that self-supervised learning can compress a training set into the weights of a model. And then these weights can be like the hidden state that tells us what to remember, what to forget. And so if we have like some RNN, like some outer loop RNN, and then within that model, at every hidden state, we have like a self-supervised model, this can learn the relationships between the data at each time step to have a better prediction of the output. So, so some more basics. The little table here. So this top one would be like the naive RNN. You have the vector, which is your hidden state, and you just have some basic update rule. And then you have some update or output rule. And then this is a constant time. So this would be a linear complexity because you have just over every time step, but it'd be O of one for each time step. Whereas self-attention, which is in transformers, you'd have some growing list, which is the key value cache. And so at every time step, you're going to iterate through some like T items in the list at every time step. So that's going to have, or that's why we see the quadratic complexity. However, with TTT, which is test time training, the hidden state is the weights of this, the parameters of some model F, which is the self-supervised model. And then we have some update rule here, which I'll talk a little bit about, and then some output rule, which is the self-supervised task. And this again is a constant time per time step, so we have a linear complexity. And this would be a lot faster than transformers. So once again, the hidden state is just the weights of this model F. And the goal is that this model can compress the long sequence into like some like hidden state that's much better at understanding like what's actually relevant to the output. And then the update rule, we do gradient descent on the model. And so we have like the previous time step here, and then gradient descent on some self-supervised loss here that I'm not going to go too much into, but essentially this F here is the self-supervised task, which is a reconstruction task. And then we do gradient descent at every iteration. So the structure of this full model, you would have some outer loop, which is the RNN. We have at each time step, you have some thing. And we can train weights for that. That'll improve the inner loop. And so there is still some training beforehand. And that would be training the model to have these, I think I have it later. So these like thetas. These are the trained parameters. And that is taken with respect to the larger network. But these can improve the self-supervised model. And so within the inner loop, we have this self-supervised model F. And so that's being trained at test time at every iteration. And then the parameters of F, we are updating at every step, and we take the gradient descent of that. Is this mostly clear so far? Yeah, I can try. So say we have some like larger RNN here. This is the outer loop. At the very beginning of the actual testing, we would instantiate some like self-supervised model F here. And then we would have some thetas that I'll describe a little bit more later. We have like the analogs of the pre-Rickian value transformers, and this is for the self-supervised model. And then, so we'd first train this outer network, but then in this inner network, we'd have, say like T equals 1 and 2 and so on. At every iteration here, we're training this new or this inside model. And then we make the output after we've done like training this again. Is that a little more clear? So the paper has a much more like in-depth explanation, but I don't want to like try to explain it back to these myself.
So there's an outer RNN which takes as input the x's to the sequence,
Yeah.
and It
So
outputs what?
it out well, so it's outputting like the prediction. I'll go back slide.
So this here is like the output would be this inside model. Um, and I don't have the actual like output rule here, like what it's actually doing in the code. But essentially the output is coming from that inside model.
Does the outer loop have weights?
Yeah. So that's skip ahead a little bit. Um, so like this theta K and then theta Q, and there's a theta V. These would be um the outer loops like weights that are improving the inside model.
Okay. So your so the outer RNN perturbs the X input in some way for the self-supervised learning task for the inner RNN,
Yeah,
and then you output the output of the inner RNN after you train it on that self-supervised task.
yeah. And this is also like just this is a model within a bigger architecture too that I'll explain at the end. Um, but it sort of makes a little more sense once I get to like the architecture because that depends on like what the input is. And there's some convolutions that I'll explain with that too. So then, yeah, so the self-supervised task, which is the like what the model's actually doing, it's a reconstruction task. So you first corrupt the input and then reconstruct it. And so this is, I think we talked about GANs in one of the lecture or talks. It's that same idea where you have some input and then you add noise and then reconstruct that. And I don't know much about this part necessarily. I'm not too familiar with the self-supervised part of it, but this is essentially what the model is doing on the inside. And there's also a variation to this. You can like change it up to have a different task. And this is also part of the authors said to they want to improve the model by testing different tasks, but this was not part of my work. And I'll get to what I was doing too. But essentially you have some input, x of t right here, and then the outer loop parameters, or one of them is theta k. And so then that gives you the corrupted input. And then you reconstruct that with this theta v. And again, you learn this theta k and v in the outer loop. So these are the hyperparameters of the like outside model. And then you use them inside the inner model to improve this inside model. And then we take the loss on this inside model here by doing this line right here. So then the output is this. Yeah.
Do you, so for the label, do you compute label from the same input as the, the direction, right?
Yeah, it's the same input x of t. Is that?
Theta V is,
Yeah, theta v and k are both learned in the outer model, but they're used in this inside self-supervised model.
So in a way, you're almost to the supervised learning the outer model, you're essentially teaching it how to train the inner model in a self-supervised way.
Yeah. So the idea is like once you had finished training your outside model, these parameters would be designed to help the inside model do its task. So the a big part of this is training the outer parameters to like essentially fit your self-supervised model. And again, you can like change this, so then you change your like the training part of it. But it all depends on what the inside model is doing. Yeah.
this might be like a dumb question, but why do we need like a theta V label? Why not just like try to reconstruct the original?
I think it's just a matter of if you try to like do more to it, then that increases the like cost and time. So they just chose like a really basic self-supervised task here. So you could do more as
Well,
far as like
I mean, it wouldn't reconstructing the like input just xt like be an easier task than, or I guess maybe adding an extra.
I guess I haven't thought about that, but I think my best guess is that it's a thing of like efficiency and like the um like you could do more to make it like a better loss function, but it's also at the risk of like you're doing this at every time step, so it'd take longer or potentially longer, um, and more memory and resources. So it's a thing of keeping it simple on the inside so that it doesn't grow too much.
What's the objective with what's the loss function for the outer open?
Um, I don't
How do
actually,
you optimize theta v and theta k?
I don't actually have that. I think they described that in a paper that's like earlier than what I'm talking about, so I'm not actually sure. And then so this is the output where you have this last theta, which is theta q. And again, these the q, k, and v are analogous to the transformer ways of query key, the query key and value matrices are tensors. And then so this is the test view, this is the output that you have. So then this is good, but again, it's a sequential thing. So ideally, would optimize this to be faster because part of it is that it can perform well, but we want it to be faster than transformers. And so one thing the model does or can do is parallelize a certain number of steps. And so without going into too much detail, um, we take the gradient of like some W0, which is like the hidden or the initial hidden state, and then we do it up to some time steps B, which is also a learned parameter in the outer model. And so like a traditional RNN, you would just take the gradient at every time step, so it depends on every previous one, and then you can't parallelize that. But in this case, we're taking them with respect to like some fixed number B of previous time steps. So it's not necessarily perfect, but it's functional for the sake of maintaining a high accuracy while also speeding up the computations. And then there's also, they talk about mini batch gradient descent, which is also another way to speed this up, but it's not necessarily relevant to the main idea of this. So I didn't go over it. But so there's just basic batch gradient descent. And so we take these gradients with respect to a fixed number of previous hidden states or hidden state. And then we compute these in parallel. So then this is just like the idea of the RNN model, and we fit it into a larger architecture. And then we also can further, like we can stack those further. So this is just like one small part of the larger architecture. But so one thing they did here was they put it into what's called the Mamba architecture, which is one of these state-of-the-art RNN architectures. And so you have, it's sort of like the transformer architecture where you have like the value querying key. But instead we just have like a query and value, I believe, sort of like equivalence. And then so you have some input, and you feed the entire input into some 1D convolutional layer. So this way you're learning some initial embeddings and then also shortening the input, and then you feed it into the this TTT RNN, and then you'd have some output. But this, what I was talking about, this TTT part is only this small section in here. This is actually, the SSM is something different, but essentially you can just replace the SSM with TTT, and then this is like your RNN inside this larger architecture that has some more going on here. But the main thing is that you have this 1D convolutional layer that's learning things first, and then you input it into the RNN. And so the actual input, like X of T, is going to be different from like what you input versus what the RNN sees. So what I was doing or was testing is different instantiations of this inner model F. So the authors only implemented a linear model and a two-layer MLP. And my thought was that if we could increase the complexity of this by doing like a quadratic model or some larger polynomial, or we can just increase the number of layers of the MLP, so do like 3 through 5. The drawback here, we don't know what the actual results would say yet, but as this could be better at learning more complexity, but at the risk of it could take longer because you're having more stuff going on in this inner model every time step. So this might reduce the speed. And so it's a trade-off of like cost versus, or like speed versus accuracy. And then they also talk about you could do different like self-supervised models, but this is not what I focused on. And then the end goal here is apply this kind of model, which would be state of the art, to some kind of time series data. So for example, you could have like breathing signals where it's like someone sleeping overnight for 12 hours or less, and then you have the signals at every some frequency over the night. And from these signals, you can predict some kind of output. So one example is like if you could predict if someone has some kind of like lung issue, you could see it. Well, in theory, you could see it in the data and then have your model output some result. And this would be really good for this kind of data because you have some very short sampling frequency over some long time. And so you'd have to have a model that's really good at having a high accuracy over potentially millions of time steps. And so this is essentially just the gist of what I've been doing for my work. And the TTT was the main thing that we've been focusing on. And that's all I've got, a bit shorter presentation.
What did they try their model? What did you propose about it?
Like what data set?
Like what tasks?
Um, I think they didn't actually evaluate it on specific like data. They're just more so looking at like how fast and accurate it is. And so they're like the data they tested on is it's called like the pile three and then the books data set. So just long sequences or long data with very long sequences like books or like the length of like a 300-page book, for example, or just like a website has a lot of text on it, that kind of thing. But it's not so much tuned to have some like output to like summarize what it's saying. It's more so looking at how fast is this able to train and the perplexity of this model. Yeah.
We made it let's quiet. But based on what you're doing right now, what I've asked is like, given what you're saying about making it more accurate and the trade-offs of it, have there been some using specifically that you think were like hard trade-offs you have to talk about, or maybe like things you're focusing on, like the training hyperparameters or something like that? I know for me, like when I made models in the past, like when it's not good, I'll go back and be like, okay, let's like tweak that and see if it works. Like, tweak that.
Yeah, so I'm just using like the already trained model they have. I'm just testing um like so the model's already trained, but then I'm using a different tokenizer to input like the data sets they use to see how like the speed compares and accuracy compares of like the same data sets. Although I haven't actually gotten any big picture results yet, so I can't really say if anyone's better than the rest. But I think from the paper they said the two-layer MLP had the greatest or the best performance and is better than like the state-of-the-art transformers. And it's also faster, but it gets to a point where like it's the difference of like how much better it is versus how fast it is, it diminishes as like the sequence length grows. And transformers don't have that issue, so it's a problem of like trying to learn greater complexities as the sequence length increases without also while maintaining that faster speed still. All right. Well, thank you.